Today, I want to give kind of a short introduction and overview of this kind of really exciting thing that has happened recently around what I would call generally neural signal representations and what you might have more commonly referred to as NERF or neural radiance fields. So to start with, I'm going to discuss a little bit of vocabulary. I think this will be obvious for pretty much everyone here, but I just want to make sure that when I say something, everyone agrees on what it means. So as I said, there's kind of this word signal representation in them. So what is a signal? Generally, a signal, I would think of this, it's some quantity that is varying in time and space. Roughly, you can think of it as a function from RD to RP. Some typical examples you might encounter might be, some sounds or audio signals, some, measures of humidity in the atmosphere, or, MRI, which is a measure of kind of activation in your brain. And this might be extended to more dimensions that I can draw on the picture. It might vary in time and so on. So this is kind of, roughly speaking, when I say a signal, it's just a function that is reasonably smooth in some sense. Now, given that I just said a signal is a function, there's kind of a basic question when we want to work with it in the computer is we need to represent a function, right? So a function mathematically is this infinite dimensional object, but on the computer we need a finite amount of stuff to be able to work with it, store it, and so on. And so fundamentally, to represent the signal, we need to choose some way to turn this kind of function that goes, says RD to R, into just a vector of things, right? A vector of things is what can store on a computer. The function is what we're thinking about mathematically. We'll come back to this equivalence in a bit. So how might you do it in practice? Well, one of the kind of very obvious ways of doing it is just to sample it. Right, so this might be kind of really how you think about an image. When you put an image in PyTorch or something, you get a big array of numbers. And really, what do they represent? They represent some continuous value that is evolving over space. And what you did is you took the value at a set of points on a grid or something like this. Right, so this is maybe the most common way to store SL functions. And to give you an idea of kind of the numbers we're working with, if you have about 30 seconds of audio, then you might store about 1 million points. If you take a picture with a smartphone, you store maybe 12 million points. And if you take 30 seconds of video at 1080p 60 frames per second, then you store about 62 million points. Right, so these types of things can grow very, very quickly, especially if the dimension increases. There's this kind of multiplication across your dimensions, so the number of grid points might grow very quickly. Now, as an aside, before we move to the next thing, there's kind of this question, we have this array of values and we have this kind of mathematical function. The array of values is kind of defined on a discrete set of values. But mathematical function, this is a function from all of RD into some place, right? So there's a kind of obvious question is what happens if you give me an array of values and you ask me, okay, what is the value of this function at the point where I didn't sample it? What happens then? Well, we have to define what happens, but generally this process is called interpolation, and we have to make a choice about how we choose to fill in the values that are missing between the samples. And so here I drew 2 examples. What happens, I sample the green points. So the green points are the true values I observe. And then in between them, then I have a guess. And I could, for example, put a piecewise linear guess, or I could put a piecewise cubic guess, a piecewise quadratic guess, and so on. And there's all kinds of ways to guess, and they're all very reasonable. And hopefully, as long as we sample fine enough or something, these all give us approximately the same answers. And so in particular, that also means that we can think of arrays as functions just by essentially interpolating across the points. Now, I'm sure all of you are like numerical analysts and have thought about these problems a lot. And one thing is that sampling a function is not the only way to work with a function. Kind of the broadest way in which you can think about working with a function is really expanding it in terms of a basis. Right? So essentially, I'm going to have a finite set of values. I'm going to define my function as a linear combination of a set of predefined functions that I've chosen beforehand, weighted by those values I've chosen. And in fact, the sampling process, if I believe that I fill in the gaps with linear interpolation, will correspond to choosing these kind of hat basis functions, right? And I'm sure everyone has heard of the Fourier transform and the cosine basis that corresponds, which are these kind of sinusoidal functions. And these can be interesting because they can help us do arithmetic faster. The fast Fourier transform has very nice properties in terms of the convolution and so on. So there are some operations that we'll be able to do faster on those bases. Today is kind of a bit taking a step back and maybe thinking about different types of representing functions that are not these basis expansions, and we'll give up a lot of the very nice properties, but in exchange we'll get some other advantages. So finally, just a vocabulary point before we go on. I'm going to also talk about operators on signals. So just an operator is just a thing that takes a signal and transforms it to another. So it might be a differential operator. I take a function and differentiate it. And generally, it's all kinds of things when we have actual problems that we care about. If I imagine there's some signal and I observe it, then that might be an operator. The operator describes the physical process of observing it. It might depend on the instrument you use, the method of observation, and so on. We're not going to talk about too much about this today. OK, so now let's move on to kind of the meat of this talk, which is the idea of a neural signal representation. And to illustrate this, I will illustrate it by kind of the main paper that kicked this idea off, which is neural radiance field. So this is going to be a very specific problem, which is going to mean a specific signal that I'm trying to represent, and a specific operator I'm trying to use. So the problem I'm trying to solve, let's say for now, is this problem called novel view synthesis. It's given in this fashion. Suppose that I bring out my smartphone, I take pictures of some object from various angles, and suppose that for the sake of argument, I know the angles from which I've taken the pictures. So I get a big collection of images and also where they're taken from and so on. And the goal that I'm asking of this method is now if I ask from a new direction from which I haven't taken a picture, ask the question, what would a picture taken from that direction look like? Right, so I've taken pictures from a bunch of directions, but not from this direction. And now I ask the question, what would it look like if I took a picture from there? Right? And so this is the problem that we're trying to solve. And really, the framework we're going to think about is the following. We have a signal. The underlying signal that we have is essentially the signal in space that represents the radiance or the amount of light emitted at each point in space. And we're going to kind of solve this inverse problem where from a number of observations, we're going to reconstruct the underlying signal. And then this is enough information for us to then render the object from a different direction. Hopefully, this is mostly clear. And if you have questions at any point, feel free to ask. OK, so how do we work with this signal? Well, the operator that forms the image, right, the way in which the image is captured in your camera, one model for it can be the following. I look at the underlying signal that represents the amount of light emitted at each point in space. And when I take a picture, I think for this pixel, what this pixel does is it integrates the amount of light that it receives along the ray. Right, so the pixel, due to the optics, looks in the ray as a straight line, and then just integrates the amount of light that is received. And then there's another term which has to do with the opacity. So light doesn't go through every object. So if it stops here, then it doesn't see anything that's behind it. So essentially, when we think about it, this is the underlying operator, is that it's integral from 0 to infinity, so from my camera to all the way to the end of a transmittance function, which tells me how much of the light at this distance comes through to me, the opacity, which is kind of how much this point contributes, and the color, which is what is the actual amount of light emitted at this point, RGB light. And we can describe all the points. So this gives me a relationship between the image I take and the underlying signal, which is the 3D representation of the object. And armed with this, I can actually just do the deep learning thing and try to solve the problem. The last thing I need to do is there's a question, how do I represent the signal itself? Right? I've kind of talked in a very abstract fashion about these functions and integrals and so on. But as we know, to get this to run on a computer, I need to make some choices. And here the choice is very interesting. The choice we're going to make is we're going to see a function, right? We have this signal, which is a function, and we see a function. And because we're deep learning people, we're going to just replace a function by a neural network, right? A function I don't know, just throw it out, put a neural network in there. And we're going to put a very simple neural network, actually. We're just going to look at the input parameters, throw it into an NLP, and predict the components, which are the opacity and the RGB color. Right? So just do this. And what do you get? You get something like this. So this is the reconstruction now. I've re-rendered from all possible directions, and I see something like this. So it turns out that this simple idea works extremely well. And today, I want to kind of walk a little bit through all kinds of ideas that spawn of this. I'm not going to go necessarily into the details of how you do this. In fact, in hindsight, it's super easy. I'm going to discuss it a little bit. But I want to kind of explore a lot of the possibilities that people have come up with since we started this. Yeah.
So how does it depend on, so if I have pictures from, say, like a certain cone looking at the bench, and you're kind of circling the cone with this little motion, how would it compare if I asked it to kind of go to the other side of the bench where it has no photos of? What's the difference between like interpolation and extrapolation in that sense?
Yeah, that's a very good question. It can extrapolate to some extent, but obviously the quality will be worse. It really depends on the amount of things. So people actually study two scenarios. One is the forward-facing scenario, where you mostly have pictures from direction, and then one is kind of the 360 scenario. And they also have different characteristics. But obviously, for this is mostly learning from a single picture. It's not like we've taken loads of pictures of loads of stuff, and we learn across them. This is we're solving this one specific problem. The object is kind of here in the moment. So people have tried also more things where there's more shared information, but for this one, there's no shared information. We're solving one problem at a time. OK. And as I promised, just a quick note on training it. It's super simple. Essentially, what we do is we have our data, which are pictures that we've taken from a given direction. So for a given pixel, right, I know exactly where it was taken from and the ray, kind of the direction into the volume that I'm going into. So what I do is I look at the nerf, right, which is my neural network parameterized by W, and I compute the sample points, right? So I had this integral that was my operator that said, like the curve, my pixel is the integral of the light emitted along this ray. Obviously, you can't compute a full integral on the computer. You're just going to sample it and do some quadrature. So I say we do some quadrature with TI, right? And we sample the opacity and the color. Now we compute the predicted pixel value. So instead of having an integral, I have a sum, but otherwise it's the same quantity here. And then I compute the log likelihood of a pixel, and I'm assuming they have a Gaussian camera, so the noise is Gaussian, and the log likelihood given the average value is just the square loss. And now, I'm done. I have computed loss, just backpropagate. Everything we did here, completely differentiable. Yeah.
One question. So your input is not just the image, right? You know the distance of the object and the position of the observer and the object, right?
Yes, I know exactly where it's taken from. I know the kind of parameters of the camera. That includes the optics, the field of view, and so on. But actually, we'll see next that people remove these things. You can actually just learn them with everything else. So if you don't know them, put them as unknowns, do gradient descent, and it still works. Okay. But yes, in the simple setup, we assume that we know exactly what the camera looks like. OK. The interesting thing to point out here is that I do not need to explicitly invert my nerf. What I mean by this is that if I think of nerf as a way to represent a signal, right, typically if you think of a basis, you need a way to go from the basis gives you a way to evaluate a function at a given point. Right? If you give me expressions on basis, I tell you, can you evaluate the function at x equals 2? Well, you just sum up over the basis evaluations, and that's fine. But the other way around, if I give you a function, say sample, then I ask you what are the values of the basis, you need some kind of transform for this. Now for the nerf, and for these kind of learning strategies, there's no easy way to go from a given function to what are the weights of the neural network that would spit out that function. There's no easy way to do this. Right? There's not a DCT or a DFT or something like this. But it turns out that because we're using gradient learning, we don't really need this. We just need a forward model, and the gradient takes care of the rest. OK. So now I'm going to go through some examples and applications. If I endpoint, I'm going to kind of have a very quick overview of them. If I point like, this is crazy, this is impossible, I would like to learn more about how it's done, I'm very happy to answer. OK. So there's kind of a few knobs that we can tweak on the nerf. One question is how can we build the neural network, right? The underlying neural network that predicts the intensity of the light and the color at each point in space. How should we build it? So the original paper built it by using essentially a frequency encoded MLP. So what it did is that took each of the positions, x, y, and z, expanded them in terms of a Fourier series, and then just fed these big vectors into an MLP, and then it's a two-layer MLP that just predicts the color. So that turned out to work fine in practice, but nowadays we don't use this so much because it takes too long to learn. It's very expensive to learn because essentially what happens is that you have a global dependence between all your weights and the output. So it was a good idea to start, and nowadays not used so much. What have we moved on to? We moved on to all these kind of slightly more explicit scenarios. So you can kind of, instead of having this kind of completely Fourier-based approach, you could have a very simple interpolation-based approach, right? Why are we even bothering with a neural network? Maybe we can just have a volume, and we sample in that volume using, say, trillion interpolation at a given point, and just evaluate that. And maybe feed it through a neural network at the end. And the reason why you might want to do this is that it can allow you to create edges, whereas with trillion interpolation, you'll have a very hard time creating edges. So it turns out that if you do this correctly, and you kind of do a little bit of work and getting things to run really fast, then you can get really good results, and that's what this paper did. Now, this is kind of still very basic. One of the issues, of course, is that if I have a big tensor in n cubed, then as the resolution in volume increases, I'm going to spend a huge amount of memory, and we don't have that much memory on GPUs, so that's going to be a problem. So for example, one idea you could try to address this would be to try to have a low rank representation of the volume itself. So this is what this paper does, TensorF. They decompose the big volume, right, which is an n cubed, as some kind of low-rank decomposition. And again, a three-dimensional tensor, you get some flexibility in the low-rank decomposition. Right? There's not one way to decompose a 3D tensor, but they just put a bunch of them in. You might say, well, this is not invariant and so on. Doesn't matter. As long as you run the gradient descent, it'll be fine. So they do kind of these kind of component-wise decompositions and then these kind of plate vector decompositions. And just do it, and it runs perfectly fine. And you save a lot of memory by going low rank instead of going full rank for a three-dimensional tensor. So it's also pretty successful. And now, kind of maybe the evolution of all this is probably this currently the most successful version there is this instant NGP. The setup is a little bit too complex to explain on the side, but the basic idea is, again, we had these volumes. But again, we don't want to store all the pixels in the volumes. So what we're going to do, we're going to randomly force some pixels to have the same value. So instead of having n cubed of them, we're going to have 100 of them, and then we're going to say the first one goes to the first one, and the second one goes to the second one, and randomly switch them together using a hash function. And say, this again sounds, randomly enforcing pixels in your volume to have the same value. How could that ever work? But it turns out that with the power of neural networks, it works just fine. And this is probably the most commonly used architecture nowadays especially for all these NeRF image type of things. Okay, so that was kind of, how can we build a signal itself? But then there's the flip side, which people have been exploring more and more, is, right now we're doing something very pedestrian with our signal. We're thinking the signal just represents the amount of light that's emitted in three-dimensional space. But there's much more that we can do with it, right? We can think about, representing a wider variety of signals than just the amount of light that's emitted at each point in space. Okay, so what type of signals can we represent? The first one is we can add some latents. Right? There's no reason why the signal itself should only represent a three-dimensional thing. Right? We know that in the real world, your signal might vary. For example, here it varies with the time of day. And so what you do is, instead of thinking of your function as a function of three-dimensional space, you can think of your function as three-dimensional space plus some latent parameters. Right? And you might say, well, we don't know what the latent parameters are here, and this is exactly true. And this kind of comes back to Bruno's question. What if we have latents that we don't know, say the camera pose or something? Doesn't matter, just learn everything, right? This is the deep learning way. So this is an example of where they did this. They take all kinds of photos taken by tourists, so they don't know the exact camera that was taken, they don't know the exact direction that was taken, there's some divergence in the time of day and so on, and then they essentially learn two networks. One network that's kind of shared between everything, and one network that kind of is able to count for small deviations. And then you learn that well enough, and you're able to kind of produce things like this, where you can control, to some extent, the aspect itself. So this is a pretty powerful idea that also has been useful in science. You can also stitch blocks together to create these super large nerves that span city blocks or even like the whole city. So this actually now means something that it's built into Google Maps. Google Maps is starting to use stuff like this to do some of the street view stuff. So this has been pretty successful. There's no reason why you can't just have the color itself. You could try to include other types of signals. So here, what we're doing is we're including a semantic signal. So it's not a continuous signal, it's a categorical signal. So our function itself just predicting the color, and the opacity also predicts essentially a one-hot value that says what type of background it is. And then based on some very sparse labels, it can kind of color the whole thing. Right? And it's easier for the nerve to do it than just to do it from the image, because the nerve perceives depth. Right? So even though it might not be too obvious from an image perspective, when you have an object that's in front, that it might be a different object, once you see the 3D picture, then it's very clear that that object is detached from the background. Finally, you might want to have something more structured than just a volume that's kind of very amorphous. So for example, a big investigation that people have been doing in graphics for a while is this idea of sign distance field. So a sign distance field essentially defines a surface through the implicit equation f of xyz equals 0. And the advantage of this is that you can easily compute, for example, the normal of the surface by looking at the gradient of f. So this is what they do here. They use the same technology underlying all the nerve stuff, but instead of directly representing the function that represents the amount of light in each point space, the function represents some kind of distance to a surface. And so that allows you to get out normals and all the stuff like this. That would be difficult to get from just a volume representation. Okay. And to train this, then, because we're in the surface and so on, you need to constrain the gradients in some fashion. So you can kind of add additional loss terms and so on to your problem. And again, because we're using backpropagation, we can handle a pretty wide variety of losses. And finally, of course, a natural thing would be to even extend the number of dimensions. So this is something that's been very, very popular recently, this idea of a dynamic nerf, where the underlying signal changes maybe as a function of time. So video, for example, is very popular, or the latents that we've also seen. Okay. So this was kind of a taster of the type of problems that people have discovered that they could apply kind of this idea of a neural function representation to. And these, mostly because NERF was first discovered in computer vision, mostly are in the domain of computer vision. To finish up, I want to discuss a couple of applications that are more in the context of science, and I think where it can really help us here. Okay. So the first one is kind of the vision problem, but scaled up for science. Right? It's NERF for general inverse problems. Why do I think that NERF can be an interesting approach for inverse problems? The first thing is that it has pretty favorable memory scaling. So instead of having to represent a dense grid, which can be very expensive, it's the graphics people have done a lot of work on making sparser and making them more memory efficient. So it allows us to represent very high, dimensionality, high accuracy grids in 3 dimensions or 4 or 5 dimensions. We've seen it with the latents. They even go to like 10 dimensions without too much issue in terms of memory, which you can then put into a GPU, which makes everything run much faster. The second thing I think, which is sometimes overlooked, is that the NERF has an inductive bias towards really spatially reasonable signals. So one phenomenon you might be familiar with, especially, for example, in Fourier basis, is this Runge phenomena, where the basis has some things that are not so nice about the interpolation itself that creates wriggles. The NERF is completely in spatial domain, so there's no issue like this. It has a very favorable inductive bias. The representation is very flexible, so you get to try off different things. And also, it kind of very naturally does coarse-to-fine sampling. So the NERF itself is a function, so I can sample the function with 1 point per angstrom or with 10 points per angstrom, and there's a natural kind of trade-off that I can do there throughout training that doesn't require me to resample my grids or anything like this. Now, the two downsides and the two things you need to have is that, one, you really need to have the operator written on the sample signal. So if you have differential operator, for example, that might be more expensive than just writing the differential operator for the Fourier signal. And second one is that really you need the GPU to work on these things. If you don't have a GPU, then this is going to be way too expensive. The GPU really helps us brute force some of the stuff there. Without the GPU, you would have to resort to fast Fourier transform or something like this, which is kind of a different approach. There's another application that people have kind of been pushing recently is the idea of using a NERF just for data compression. So a NERF might be a good representation for a high-dimensional signal itself without doing any kind of learning or inverse or something like this. So in this paper, what they did is they looked at climate simulations, which are essentially 14-channel signals on the sphere, and then they said, OK, let's put the whole thing into a neural network. And they were able to achieve 300x up to 3000x compression, and then they ran the same kind of learning problems they had on the compressed data versus the uncompressed data, and the loss was minimal. And this happens to be a good way to write compression algorithms. Can you beat them with hand-tuned compression algorithms? Yes. I don't think we're necessarily going to see images or videos compressed like this soon because we spend so much time on images and videos. But if you think about the amount of engineering you're able to spend on the signals you care about versus the amount of time people spend on designing AV1, then it might be a good compromise for the types of signals we deal with since we don't have that much time to spend. It has the advantage of being able to leverage inter-channel correlations, and it's kind of adaptive decoding. So if I don't only want to know the signal at some small point in space, I can just decode the NERF there. I don't have to decode everything else. So yeah, and the advantage is, of course, we don't need to do so much feature engineering. It kind of learns most of it for us. And finally, this is a kind of maybe a crazy application that people have been doing recently, is that NERFs actually have proved a good way to do these kind of 2D to 3D synthesis problems. So you might have seen these kind of text to image. I write mid-journey and so on. I write some words, and then it turns a 2D image. And people have been thinking, how can I do that in 3 dimensions? Of course, one of the issues in 3 dimensions is that you have no data, right? There's not a large sample of 3-dimensional images or 3-dimensional meshes and text together. People take pictures all the time, but we don't upload 3D models all the time. And so people have been using NERFs as a way to convert essentially a 2-dimensional picture into a 3-dimensional rendering by showing it some pictures and doing some tuning and so on. This paper is actually pretty complex, but you can see that it does something interesting there as a way for us to bridge the gap between 2D and 3D. And finally, let me just mention kind of some of the work that's been happening in cryo-EM, which is kind of something I'm working on. So for those, the cryo-EM is an inverse problem. You see something like this. And the image formation process is essentially a projection, and then there's an in-plane convolution with an oscillatory function that's called the CTF, and then there's a bunch of noise that's added. And so one thing that has been kind of very interesting here, and that people have already started applying, is the idea that we have this heterogeneous problem. So the signal we want to reconstruct is not just a three-dimensional signal. It's a three-dimensional signal that might have some latent parameters that vary, right? And this is very difficult to encode classically, because the way in which it varies, well, if you try to encode a five-dimensional, six-dimensional signal, then you're going to run out of memory very, very quickly. And so nerves have proven a very good way to encode these kind of latent parameters and do something about them. And you can even use variational inference and other types of amortized inference to do interesting stuff there. OK, so to conclude, some ideas about the futures of nerves for science. Generally, I think if you happen to have a problem where you're using some kind of gradient-based inference and a GPU, I would give it a try if you have signal. I think it's a very interesting basis. It bypasses some of the issues. And if you do, just use instant NGP, and it's the best nerf. In terms of really what it provides, in my opinion, is really the flexibility and ability to iterate very fast. Because you're in this kind of gradient-based learning system, you don't have to come up with a custom inference strategy for each representation you try. And this really has been the strength of nerves, is that people have been trying all kinds of stuff that maybe shouldn't have worked, but some of them you tried and it actually does work, and this is amazing. Right? All of the ideas that I presented, they had no reason to work, but we tried it and it worked, and this is really kind of where the flexibility comes in. And finally, I think we're still at the beginning, especially in science. There's probably many underexplored applications. So compression, I mentioned people are starting to think about this, but this is kind of very underexplored. I think there's also a lot of opportunities for unsupervised learning. So as mentioned earlier, currently, when I train a nerf, I share no information. I train a nerf just on data I see here. But I can imagine if I have different sets of data, I could train a nerf and try to share some information and keep some information private, and the information I share, I can try to learn latents across or something like this. So that could be something interesting. And finally, you could try to amortize the nerf itself, and that, again, could give you some interesting insights into the statistics. Okay. Thank you.
So we have time for a question. Yeah.
Thanks for your talk. You showed.
Sit mic, please.
You showed the night to day transition. So I'm interested in the identifiability of the latents, how they separated, how they disentangled the viewing direction and position, and was that in the forward model itself that explicitly modeled that?
Yeah. So some of the latents are explicitly modeled in that the view direction and so on really comes into the physical model of the image formation process, because we're explicitly saying the ray comes from here and integrates along this. This is disentangled from kind of the view parameters of the image itself, which come into essentially saying that the function that represents the amount of light that's emitted at each point of space, this has initial latents. Now, those latents, that will be more tricky to disentangle, right? Like, imagine you have night to day versus rainy, not rainy, then disentangling this will be a big challenge, and certainly something that is open question. I think there's interesting questions to ask there around, if we learn something with a lot of latents, how do we disentangle them? It's a big problem in cryo-EM.
So the appearance is sort of like everything left over after you've modeled.
Yes.
Viewing direction.
Yeah, exactly. Because the viewing direction happens to be modeled very explicitly through like a physical camera model. So for example, actually, when we do the cryo-EM, we model not just the view direction, but we also model some parameters that have to do with the way the weak scattering is propagated and the propagation and the interference that causes there. So that will be modeled explicitly. But then there's some remaining stuff that you can't model explicitly, and that disentangling all that is not so obvious.
So there is a question from Zoom. So from Linquin Zhang, could you say a bit more about inductive bias? I'm trying to understand what makes nerves work so well from very sparse sample of the original signal. Related is how important is the choice of operator from them to be effective?
Yeah, so inductive bias, I think, has all to do with how we construct the nerves that are successful, especially these nerves nowadays. If you read this paper, you'll see that it's constructed based on this idea of a multi-scale grid. So you have a very smooth grid, and then you have finer and finer grids, and they combine together. And so generally, this seems to be a pretty good inductive bias for spatial kind of like signals that we care about, in that they're mostly like compactish, smooth-ish in some extent. Maybe they have some edges and so on that the nerve is able to adapt well to. So my current belief is that for most spatial-ish signals that you have, nerves are very good inductive bias, certainly better than most of the basis that people might typically use that I think are a bit too on the spectral side. In terms of the operator itself, my impression is that the operator is actually pretty flexible as long as you get a reasonable coverage in terms of your gradients. Something that I was reading today, actually. In this paper, they mentioned that one of the operators they use involves some gradient, and they take the numerical gradients in order to be able to backpropagate it through more points in the nerf rather than taking a kind of backpropagated gradient. But my impression is that the operator is very flexible. We've had quite a lot of success with like cryo-EM operators, which are these weak scattering operators, which are pretty different from optical images.